Hey everyone. So this lecture is going to be fairly short. It's on Thomson 7.3, which is called form factors. I think it's really good that he put this in a separate section just so that we get you used to the idea of these form factors, because this is usually probably not used in a lot of other science classes. Well, I may be wrong about that, but this may be the first time you're dealing with a system that's complicated enough that the best way to deal with it is to solve the simplest version of it first, and then multiply by these things called form factor to correct for it. So these form factor are kind of corrections to the things you are approximating. Well, the things that in your first order approximation you don't get. Okay, and that's just a correction to it. It's kind of a both experimentally and theoretically is nice, because then whenever the theorist can make a correction, then you can actually see if that shows up in the experiment by factorizing these things. Okay, so in the previous section, when we deal with electron proton scattering, right, so we have an electron come in, electron come out, right, here's the particle line, you have the little gamma photon exchange between them. And the proton, right, was treated as just a point-like object, right? And so all we care about is like, what was the charge on it, okay? So this treatment, right, if you think about the proton, it's not a point-like object, but what we did, I'm going to draw a more physical picture of a proton first, right? Maybe a circle like this, right? There's a bunch of stuff in there, but right, this thing has a total charge of +1. But this total charge, right, is actually not just at the center of the proton. Hopefully that makes sense, right? If you have a proton, there's will be some charge distribution within it. What we did in the first 7.2 is that model that, right, as if it's just a point charge with no size, and all the charge is in the center of that sphere, okay? So that's the point-like model, okay, where the charge density, this thing called rho, right, it's just like, one particular part with some width to it. Well, with no width to it, it's just a point-like particle, okay? This works, right, in the low momentum transfer regime, right, where the wavelength of the photons that's being exchanged between the electron and the proton is much bigger than the radius of the proton, okay? Remember, this is the Rutherford and Mach scattering, okay? So we covered last section. What we're going to do in the next section, we're going to go to better and better approximations of actually what's going on with the structure of the proton, where instead of approximate it as a point object, we're going to approximate it as like a sphere with some charge distribution, right? So as opposed to just a point charge, right? Each of these pluses is not representative of one charge, right? But the charge tends to be larger towards the center, a little bit less, right? In fact, the model is actually an exponential decay of how the charge distribution are distributed. In fact, you can find this in a textbook. Well, it's called Fundamental Physics. Don't worry about it. You don't have to get it. Fundamental of Nuclear Physics, okay, where people actually measure the charge distribution of a proton. So on the left panel here, we go to red, okay, this is the charge distribution of a proton, where it goes up very fast. And the reason that is, this has to go to 0 at radius equal to 0. So this is what we're plotting here, the radius out, right? At the center, right? Technically, this should end here, at some finite number. But what happened is that you actually cannot measure that well. So the people just, make best fits out of it. So, but don't worry about this little gap here, okay? But what happens is that it kind of decays, and it has a little bit of structure here, right? But most of it is approximately an exponential decay, okay? That's what we're going to model it as. There is this, kind of edge effect here. In fact, right here, 0.877 femtometer is actually the radius, the mean radius of the proton. This is where we think about the proton actually ends. Okay, there is some charge remaining outside, because you know that all these objects are not like finite, discrete things. There's some fuzziness to it, right? Okay. This plot also showed the neutron version. We're not going to deal with the neutrons since we're not scattering neutrons, but hopefully you see that the charge distribution is actually positive, right, inside, and then negative outside, and then the whole thing is just neutral afterward, because the integral has to add up to 0 because the net charge of 0 should be 0. In section 7.5, we will talk about the magnetic moments, but let's just not deal with that for now. Okay, so in order to account for the charge distribution, right, in our calculations, okay, what we're going to do, instead of trying to, redo all the calculations, right, with our Mott scattering that we used in 7.2, what we're going to do is instead modify the answer we got by this thing called a form factor. Okay, in fact, that's what's written over here. Okay, F sub q squared, where this is the 3-vector q. Okay, just be a little careful. Why is it the 3-vector q instead of the 4-vector q? Right, this is actually what's known as a Fourier transform, okay, of the charge distribution. Okay, so this form factor function is a function of the 3-vector q squared, which is the momentum of the exchange particles squared, okay, and it's an integral of the charge density to times eiq dot r, okay. So some of you might recognize this as a Fourier transform from your math physics class. If you don't worry about it. We're not going to deal too much with it, but just to know why this form factor depends on q squared as opposed to the 3 momentum q as opposed to the 4 momentum q, because you are basically integrating the effect. So let's say you have, right, I'm going to draw the picture we have up top again, right, you have some charge distribution as a function of r. Let's just, project it into the radius coordinate, right, and you have some shape to this. What you're doing is you're doing an integral of this so that it figures out the cumulative effect of having a charge distribution as opposed to a point-like object. Okay. There are other models of how to model these charge distribution inside a non-elementary object, right? So in the case in 7.2, we model the proton as a direct fermion, meaning what it is just a point-like object. Okay, so what happened is that this integral actually just gives you a flat function. Okay. For the proton, what we're going to do is we're going to model it as an exponential decay, and then it's going to turn into this thing called dipole with the parentheses. Okay, it's actually not a dipole. Okay, but then larger nuclei, right, is going to, instead of an exponential, it's going to be modeled as a Gaussian because you have multiple little nucleons inside it. Okay, you can model the charge distribution as some uniform sphere. This is a very macroscopic thing. Like, so if you have a giant sphere just full of charge, charge sphere that we see in class in introductory physics, right? You'll get this what's known as a sinc function instead. Okay. For metal, so this is for calcium 40. What happened is that the electrons around it, the protons in the within the nucleus, they're going to form themselves around this thing called a Fermi sphere, and this is where the Fermi function comes from. But we're not going to deal with anything as complicated as a calcium nucleus. Okay, but that's the idea to these form factors. The idea is that instead of redoing all the calculation again, what we're going to do is we're going to take the same answer as before, multiply it by this form factor thing, where this form factor thing is going to account for the charge distribution inside the proton.